This is the electrostatics topic. The first section is called elementary charge. What I'd first like to do is explain a little bit about the difference between electrostatics and the next topic called current electricity. If you look at the word electrostatics, you see that you have the word electron here and the word static, which means not moving. Now, I don't want you to think that electrostatics means that the electrons are not moving. They absolutely are moving when we study electrostatics, but they are moving without the necessity for wires. For example, if I take a piece of fur and a rubber rod and I rub the rod on the fur, electrons move from the fur to the rod. We say that electrons are transferred from the fur to the rod. The fur, which has lost electrons, has become positively charged, and the rod, which has gained electrons, has become negatively charged. We now have two charged objects. The fur, positively charged, the rod, negatively charged. One of the things we'll be talking about in the electrostatics topic is how objects behave when they are charged and you bring them near each other or they touch each other. How do charged objects affect each other and how do they affect neutral objects? And again, the movement of the electrons in the electrostatics topic happens without the need for wires. As soon as we start talking about electrons flowing through wires, that would mostly be current electricity, and that would be the next topic. So, let's move again into electrostatics. Now, what exactly is charge? Well, probably the best way to describe what charge is to describe how charge behaves. Charge, first of all, is a property of matter. Matter can be charged. Energy cannot possess charge. Energy cannot be charged. Only matter can possess charge or be charged. And how does matter behave when it is charged? Well, if the charges are the same, such as positive, then those objects, whether they're two tiny little protons or two charged objects that you can hold in your hand, will tend to repel each other. They will push each other apart. The same thing would happen if the two charges were negative. This is why we say like charges repel. Charges that are the same, like charges, repel each other. They push each other apart. And again, you define charge based more upon how it behaves. Now, what about opposite charges? What if one of these objects was positive and the other object was negative? Then how would they behave? Well, opposites attract. You know that. Opposite charges attract. So that means that this negatively charged object will tend to pull toward the positively charged object and vice versa. And Newton's third law, by the way, applies. The magnitude of this force is equal to the magnitude of that force, but opposite in direction. We'll make that one negative. Okay, so again, Newton's third law is going to apply, and opposite charges are going to attract each other. All right, so again, we're mostly defining charge based upon how charged objects behave. Now, what is the unit of charge? What's the symbol for charge? Well, the symbol for charge is lowercase q, the letter Q. The unit for charge is capital C, or the coulomb. The unit for charge is capital C, the coulomb. Now let's talk a little bit about what exactly the elementary charge is. The elementary charge. What exactly is the elementary charge? Well, it used to be the smallest charge that we thought could possibly exist. Now, when you get to a topic called modern physics, you're going to find out that now we know that you can have 1/3 or 2/3 of an elementary charge because there are smaller particles called quarks. We're not going to talk about those today. When you get to the modern physics topic, we will talk about those. For now, we will talk about the elementary charge and the small particles that have exactly one elementary charge. So, what particles have exactly one elementary charge? Well, as soon as a question mentions an electron, a proton, or a neutron, always go straight to the front page of your reference tables because there's information there about electrons and protons and neutrons. There are numbers that you might have to use to answer the questions. So, for the electron, on the front of the reference tables, it tells you that one elementary charge, the charge on an electron, right, would be 1.6 times 10 to the negative 19 coulombs. You have to put the negative in front. You know that electrons are negatively charged. The mass of the electron, listed on the front of the reference tables, is 9.11 times 10 to the negative 31 kilograms. For the proton, and I'll draw the proton a little bit bigger because the proton is much, much heavier than the electron, the charge would be positive 1.6 times 10 to the negative 19 coulombs, and the mass of the proton, 1.67 times 10 to the negative 27 kilograms. The neutron is slightly more massive than the proton, but on our reference table, it lists it as the same mass because it's only to three significant figures, 1.67 times 10 to the negative 27 kilograms. The charge of a neutron is, of course, 0. So again, this is the information for the electron, the information for the proton, and the information for the neutron, which is found on the front of the reference tables. Now, this number, 1.6, we'll take the absolute value for the purpose of discussion. 1.6 times 10 to the negative 19 coulombs, 1.6 times 10 to the negative 19 coulombs. Right? This number is called one elementary charge. Again, look on the front of your reference tables. The symbol for it, right, it's one elementary charge. The symbol for it is lowercase e, and it is equal to 1.6 times 10 to the negative 19 coulombs. That is the charge on an electron. Remember that it's negative. It is the charge on a proton. Remember that it's positive for a proton. Now, how do objects become charged? Well, first of all, you know that atoms are generally neutral. A lithium atom, for example, Li(7,3), has 3 protons, 1, 2, 3. I subtract and find that it has 4 neutrons, 1, 2, 3, 4. I make the neutrons neutral and a little bit larger because they're a teeny bit heavier than the protons. The atom is neutral because it has the same number of electrons. Here's 1, 2 electrons in the first shell of lithium, and here's 1 electron in the valence shell of lithium. So, an atom, by definition, is neutral because it has the same number of protons, 1, 2, 3, positives, and the same number of electrons, 1, 2, 3, negatives. So, 1, 2, 3, 1, 2, 3, they cancel, 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 and the atom is neutral. So most of the objects around you are neutral because atoms have the same number of protons and electrons. Now, what happens if an atom loses an electron. Let's say this electron gets taken away. We rub the lithium and that electron gets taken away. Similar to the way that the electrons were transferred from the fur to the rod. The fur lost electrons, the rod gained electrons. If I take one electron away, then the lithium atom has 3 protons and 2 electrons. So now those cancel, but the lithium has a charge of +1. Similarly, there are atoms that will gain electrons, right, and become negatively charged. Now, we're not really going to be dealing with atoms in this way. That's more in the realm of chemistry. We're simply going to be talking about electrons being transferred from one object to another object. We're not going to worry so much about the atoms. So, when an object has the same number of protons and electrons, 5 protons, 5 electrons, then that object is neutral. If that object loses electrons, now the object has excess positive charge. In this case, +2. We say excess because these cancel, and because he lost 2 electrons, this object now has 2 extra protons that are not being canceled by electrons. This object is positively charged, +2. What if the object had extra electrons? If the object had 1, 2, 3, 4, 1, 2, 3, 4, 4 protons and 4 electrons, and gained a bunch of electrons, let's say 3, now the object has excess electrons. It has more electrons than protons. So these cancel, and the object now has an excess negative charge. The excess negative charge in this case is -3. Now, what about the unit of charge that I mentioned earlier? The coulomb. How does that come into the discussion? Capital C. Well, if you have 2 extra protons, and each of those protons has a charge of 1+1.6 times 10 to the -19 coulombs, then the total excess charge you have in coulombs is 3.2 times 10 to the -19 coulombs. If you have 3 extra electrons, all right, I'm going to get rid of those there. We'll just say the whole number 2 and the whole number 3. If you have 3 extra electrons and each electron has a charge of -1.6 times 10 to the -19 coulombs, then the total excess charge in coulombs is -4.8 times 10 to the -19 coulombs. So if you take the number of electrons or protons that are extra and multiply by the elementary charge, the charge on 1 proton or 1 electron, you'll find your total excess charge. We can develop this into a little equation that we make up on our own that's very, very handy. We can say that N, the number of electrons or protons, times, now the symbol for the elementary charge is a lowercase e, N times E is equal to the charge total. The total charge. I'm going to copy that over again up on top because I think you should learn this equation. This is an equation you're going to have to memorize because it's not in your reference tables. Take the number of electrons or protons, number of electrons or protons that you're talking about, or the number that are excess, multiply that by E, that's one elementary charge, elementary charge, and remember, that's exactly 1.6 times 10 to the negative 19 coulombs. Multiply those together, you're going to get the total charge that you're talking about, or the total excess charge that an object has. So let's try a little problem here. All right? If I have 5 extra electrons, so n equals 5, let's put my equation up first, n times E equals QT. If I have 5, those are multiplied, if I have 5 extra electrons, and I want to know what's the total charge on 5 electrons, multiply that by negative 1.6 times 10 to the negative 19 coulombs, and that tells me that the total charge on those 5 electrons is negative, multiply these, and you get negative 8 times 10 to the negative 19 coulombs. Now, what if somebody said to you that the total excess charge was a certain amount? What if instead somebody said to you that the total excess charge on an object, for example, what about the total excess charge on this rubber rod after I rub it? The rod is now negative. What if somebody tells you that the total excess charge on this rod is, for example, all right, Q total, negative 6.4 times 10 to the negative 16 coulombs. That's the charge on the rod. And what if they said to you, how many electrons does that mean the rod gained? So how would you figure that out? Well, here's your equation, all right, N times E. How many electrons is what you want to know. You want to know N is equal to the total charge. I'm going to rearrange the equation to get N by itself. All right, so we find that N is equal to the total charge divided by one elementary charge. So take the total charge, negative 6.4 times 10 to the negative 19 coulombs, divide that by the elementary charge for an electron, negative 1.6 times 10 to the negative, that was 16, sorry, 16, times 10 to the negative 19 coulombs. Do that division, this divided by this, and you find that N is 4,000 electrons. So if that's the excess charge, in coulombs, this is how many electrons were transferred to the rod. Now that's a small number of electrons, but you understand the concept. Now, what if somebody were to say to you, what excess charges are possible? Is this excess charge possible? Well, I tell you what, let's take a drop of oil. There's a drop of oil, right? Oil drop. And I'm going to put 1 electron on that drop of oil. Well, if there's 1 extra electron on that drop of oil, what would the charge on that drop of oil be? The charge on that drop of oil with 1 electron would be, all right, N times E equals the charge. So 1 times 1 electron times negative 1.6 times 10 to the negative 19 coulombs would mean that the charge on the oil drop is negative 1.6 times 10 to the negative 19 coulombs. What if there were 2 oil drops on, 2 electrons on the oil drop? Then it would be 2 times negative 1.6 times 10 to the negative 19 coulombs. So the charge on the oil drop because of the extra electrons would be negative 3.2 times 10 to the negative 19 coulombs. What if there were 3? Right. Negative 4.8 times 10 to the negative 19 coulombs. What if there were 4? 4 extra electrons. Negative 6.4 times 10 to the negative 19 coulombs. 5 extra electrons would mean that the total charge, the total extra charge on that oil drop would be negative 8 times 10 to the negative 19 coulombs. And I'll stop at 6 extra electrons. If there were 6 extra electrons on the drop of oil, then the total extra charge, the excess charge, would be negative 9.6 times 10 to the negative 19 coulombs. So you see that, generally speaking, multiples of 1.6 are definitely possible because it gives you a whole number of electrons. You have 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, or 6 electrons. See, you can't have half an electron. You can't have a fraction of an electron. So let me show you a total charge that would not be possible. All right, for example, would 5.6, negative 5.6 times 10 to the negative 19 coulombs, would that excess charge be possible? Would that total charge be possible? Well, let's find out. Let's find out how many electrons that would have to be. So, again, the number of electrons is the total charge divided by 1 elementary charge. So, the total charge is negative 5.6 times 10 to the negative 19 coulombs divided by negative 1.6 times 10 to the negative 19 coulombs. Do that math, and you find you get N equals 3.5. Well, can you have 3.5 electrons? No, you can't. You can't have any fraction of an electron or a proton when you talk about electrostatics. So this total charge is just not possible. To summarize, when you're asked whether or not a total charge is possible, simply take that excess charge, that total charge, divide it by 1 elementary charge, right? Take that total charge, divide it by 1 elementary charge, find out how many electrons that supposedly is. If it's a whole number of electrons, then that total charge is possible. If it's not a whole number of electrons, that total charge is not possible. All right, here's another example. Let's try this one. All right. All right, let's try this example. Let's try to figure out whether or not this total charge that I'm going to give you gives you a whole number of electrons. The total charge that they're giving you is 3.52. We'll make it negative because it's electrons. 3.52 times 10 to the negative 16 coulombs. Is that total charge possible? Let's check. All right. Total charge divided by 1 elementary charge gives you the number of electrons. If it comes out a whole number, then it is possible. Let's see. All right, the total charge is negative 3.52 times 10 to the negative 16, watch your exponents, coulombs, divided by negative 1.6 times 10 to the negative 19 coulombs. Well, what we get is that N equals 2.2 times 10 to the third. Now, you look at that and you say, If you do it too fast, you say, oh, that's not a whole number. But now wait a second. Just because it's 2.2 doesn't necessarily mean it's not a whole number. You forgot about the exponent. What is 2.2 times 10 to the third? 2.2 times 10 to the 1, 2, 3 third, okay, is actually 2200. You can have 2,200 electrons. That's a whole number. So be a little bit careful when you decide whether or not a charge, a total charge, an excess charge, is possible. If it comes out to a whole number of electrons, it is possible. If it comes out to a fraction of electrons, it is not possible. But make sure you know exactly what that number is. Now, for example, if this was 2.2 times 10 to the negative 3, what if it was 2.2 times 10 to the negative 3 electrons? Would that be a whole number? Let's try that. 2.2 times 10 to the negative 3. 1, 2, 3. That's 0.0022 electrons. That is not a whole number. That is a fraction of a whole number. So that number of electrons is not possible. So the total charge that would equate to would not be possible. Okay? Problems will come up where you're being asked, you're being given a total charge, and you're being asked, is this total charge even possible? Well, keep in mind that every total charge must be a whole number of electrons or protons multiplied by 1.6 times 10 to the negative 19 coulombs. So if that total charge divided by 1.6 times 10 to the negative 19 does not give you a whole number of electrons or protons, then that total charge is just not possible. All right, so why? Why isn't it possible? Because you can't have a fraction of an electron. You can't have half of an electron. You can't have 0.5 electrons or 0.33 electrons or any other decimal multiple of electrons. All right, so let's try some problems where we're given a bunch of total charges and we're asked, are these total charges even possible? So in trying to answer these types of questions, we need to keep in mind every total charge. Now, synonyms for total charge, excess charge, net charge, they might even say just charge, must be a whole number multiple of 1.6 times 10 to the negative 19 coulombs. So here's the equation. Take the number of electrons or protons, multiply by 1.6 times 10 to the negative 19, which is E, the elementary charge. That gives you the total charge. Meaning, if you take that total charge and divide by E, you will get the number of electrons or protons. This number that you get must be a whole number, because you cannot have half an electron or a third of a proton, etc., etc. So let's look at a bunch of problems where what we're going to do is take the total charges that we are given, divide each of them by 1.6 times 10 to the negative 19 coulombs, and see whether we get whole numbers. Only whole numbers of electrons or protons are possible. So, which of the following total charges or net charges is not possible? To decide whether or not a total charge is possible, we divide it by 1.6 times 10 to the negative 19 coulombs. So what you should do right now is pause the video and divide each of these possible answers by 1.6 times 10 to the negative 19 coulombs. All right, why don't you do that now? All right, pause the video. Okay, and divide each of these, get an answer here, an answer here, an answer here, and an answer here. The one that is not a whole number is the answer to the question, the answer that is not possible. All right, so while you had the video paused, you should have taken each of these possible answers and divided them by one elementary charge, by 1.6 times 10 to the negative 19 coulombs. All right, here, if you take 1.12 times 10 to the negative 18 and divide by one elementary charge, you get number 7, which is a whole number. So this is possible. All right, this is a possible number of electrons or protons. All right, protons if the original answer is positive, electrons if the original answer is negative. All right, now here, 4.8 times 10 to the negative 15 divided by 1.6 times 10 to the negative 19. All right, this is 30,000. And yes, you can have 30,000 electrons or protons. All right, this one here, dividing. All right, there you go. You get 8.5. All right, this is not possible. You cannot have a total charge of 1.36 times 10 to the negative 18 coulombs, because that would mean that you have 8.5 protons or 8.5 electrons if this were negative. That is not possible. All right, this one down here, you do the division, all right, and you get 3,500, which again is possible. All right, so this is possible. All right, this is possible. This is not possible. This is possible. All right, the question says, which of the following total charges is not possible? And the answer is, all right, C, this total charge is not possible. Here's another similar problem. Which of the following would be a possible net charge on an object? So here are your possible net charges. So you're going to take each of these possible net charges, divide them by 1.6 times 10 to the negative 19, and see which give whole number, which one is possible. So only one is possible, so only one will give a whole number answer. The others will be some sort of decimals, and they will not be possible. So go ahead and pause the video, do all the math, all right, and we'll see if we agree. So maybe you divided all of these possible answers by 1.6 times 10 to the negative 19 coulombs, and maybe your answers are in scientific notation on your calculator. So let's take a look at which one of these answers is possible, is a possible net charge. Now, you might look at this and say, oh, 2.6 is a decimal. No, it's not possible. But keeping in mind that 2.6 times 10 to the 5th is actually the number. Now, you're going to take this decimal, move it 5 places to the right. This is actually the number 260,000. And, of course, that is absolutely a whole number, and that is possible. So for the moment, I'm going to circle this as the correct answer while I check the rest of the answers. They should all be not possible. Let's see. All right, 4 times 10 to the negative 4 is really 0.0004. That is not possible. That would be a fraction of an electron or a proton. Definitely not possible. 6.44 times 10 to the first would be 64.4. Again, not possible. Just shy of half an electron there on the 0.4. 1.5 times 10 to the 0 is just 1.5. All right, so this net charge is possible. These 3 net charges are not possible because they give decimals or fractions of an electron or proton, which is not possible. All right, last problem. A student rubs a piece of rabbit fur on a rubber rod, and the rod acquires an excess charge. All right, so we know that in this case, the electrons move from the fur to the rod. The rod will be positive, the rabbit fur will become negative. So the rubber rod has acquired an excess negative charge. Which of the following is a possible excess charge for the rod? Here are your choices. We even made them negative, which is really not necessary. Usually we talk about just the magnitudes of the charges, but we did make them negative. So divide each of these by negative 1.6 times 10 to the negative 19 coulombs, and let's see which is a possible excess charge for the rod. So you divided each of the possible excess charges by 1.6 times 10 to the negative 19. All right, and what we got was 4¼ electrons, not possible. 24 electrons, possible. All right, so let's pick that as probably the correct answer. All right, whoop, right there. Here we have 6.1 excess electrons. I don't think so. And here we have 22.2 excess electrons. Again, I don't think so. All right, so these, all right, A is not possible. C and D are not possible. The possible excess charge on the rubber rod is negative 3.84 times 10 to the negative 18 coulombs, which would translate into 24 excess electrons.